Okay, let's start. So, this is the beginning of chapter 1 of our syllabus, EE131, Numerical Methods and Analysis. So, in this video, we will be discussing about chapter 1. And chapter 1 is just an introduction of numerical methods. So, we will discuss about the definition of a numerical methods. We will also discuss the three phases of engineering problem solving in pre-computer and computer era, and also some numerical methods and engineering practices. And the last part will be we will discuss the approximations that we will be using and what are the sources of errors. So we start with the definition. So first, definition. How do we define a numerical methods? Numerical methods. There are a bunch of numerical methods exist today, especially today because of our new technologies, emerging computer technologies. Numerical methods becomes more significant compared to the previous years because of this computer. So if we define a numerical methods, these are methods or techniques. These are techniques that formulates mathematical problems and it should be we should be able to solve them. We solve them arithmetically. So this is the main goal of numerical methods. So these are techniques to solve engineering problems, and the common for all these numerical techniques are there involves large numbers of tedious arithmetic calculations. So in other words, these are methods that are consume time and energy if you do it manually. But the advantage of numerical methods, if you apply them into computer applications, then it will be more efficient and more comfortable way to solve problems involving engineering and the same problems. So that is numerical methods. Now, the second part is, what are the three phases? So three phases of engineering problem solving, in pre-computer and now we still use that one today during the computer era. So what are these basic three phases? So the first one is formulation. So just like what we said before in the first part, when we define numerical methods, it formulates mathematical problem. So that's the first step. So in formulating these problems, we need to know some laws and relationships between the inputs and outputs that we want to compare, the results and the effects. So we need to formulate them based on the laws and concepts of engineering. So if you're interested in electrical engineering field, then what are the laws that we use in electrical engineering? You can use Ohm's law, you can use the network laws, and so on. So those are the concept that we need before we can formulate our problems. So that's the first phase. Then after formulating, now you know the laws, you know the relationships between the output and the input. We can now solve them. So we do our solution. So in pre-computer and the computer era, the formulation is almost the same because the laws and relationships don't change. Ohm's law before is still Ohm's law today. So it doesn't change. So it's almost the same with the way we do in computer era, the pre-computer and pre-computer era. The only difference now is how do we solve them, the solution part. So for pre-computer era, how do we compute them? So we don't have computers, so we do it manually. So what will happen? So we have tedious computations, a bunch of arithmetic calculations, and so on. So this means we expend more energy in solving the problems. So most of our time in solving problems is used in the solution part. While if you here in computer era, it's now different. So in computer era, we only use one program to solve our problems. We can use pre-packaged program applications to solve some complicated problems. Then the time you need to solve them is much lesser compared to pre-computer. So this is the advantage now of numerical methods when we use computers. So we can now use our time, instead of solving the problem, we can use them to the last part of the last phase of the three phases, which is we call the interpretation. So this will be the last part. So this is the analysis part. We analyzed our solutions. So the result of our solutions. So in pre-computer era, the interpretation is limited. So during pre-computer, interpretation is limited. Why? Because we expend most of our time in the solution part. But during the computer era, here, because of the programs that we can write and the computer that can execute the algorithm that we want, it will allow us to have holistic thoughts. So we can analyze our result. We have more time to analyze our result when we use computers. So, numerical methods and analysis is always, today is always in conjunction with the computer, with computer applications. So it's not only that you know how the concept of the methods, but what we do here in EE131, we will also apply them through computer programming. So I will teach you how to program them into computer application, and we will not use MATLAB, but we will be using Octave. There are some other programming language that we can use, but Octave is I think the closest one to MATLAB. Octave is the closest one to MATLAB, and actually you can run your program that you made using Octave into the MATLAB. Okay, so now let's go to the third part. So why do we need numerical methods? Why is it important? So what are the engineering practices that we do? Numerical methods and engineering practice. So these are some engineering practice in numerical methods. Number one. So why do we need numerical methods in the first place? First, we know that this is a powerful tool. It's a powerful tool. It's a problem-solving tool. So this is the greatest advantage of numerical method. It's a problem-solving tool. There are some problems that it's hard to solve without using some numerical methods. So the only way to solve them is if you apply some numerical methods. So this is very important. This is very useful, especially for us in the engineering field. The second one is some commercially available pre-packaged computer programs. So there are available now pre-packaged computer solving tools, open source. You can buy them or copy them and so on. Those involves with numerical methods. So those program also uses numerical methods. So when you use them, if you understand the concept of numerical methods, then you know how to use those computer programs. It's easier for us to analyze the problem because we know the concept of the numerical methods. So that's another advantage. The next one is if that commercially available cannot solve the problem that we want, then you can create your own. So create your own program. So if you know numerical methods, you can create your own programs. So that's another advantage why we need to study the numerical methods. But of course, before you can create your own programs, you need to study the programming language that you will be using. But as long as you know how the concept behind those numerical methods, creating those programs now will be much easier for us to do. So you need to study the concept behind. So number 4, because you need to create your own programs, now you will be forced to study those programs. So another advantage is you can learn and improve your programming skills. Numerical methods will force you to learn and improve your programming skills, because you cannot apply those methods and techniques if you don't know how to program. You don't know how to write a program. But if you know how to program, you can still improve your programming skills using numerical methods. And lastly, you can improve your skills in programming. You can also improve your skills in math. So it can reinforce your mathematics knowledge. It can refresh your knowledge in math. It can reinforce, it can review you anytime. So these are the basic engineering practices and advantages of numerical methods. So why do we need numerical methods? Then the last part of chapter 1, so this is the last part, the main part, number 4, approximations. And sources of errors. In numerical methods, numerical methods is a non-exact solution. It's an approximate solution to problem solving. So we don't have any numerical methods that will give you an exact value of the solution. It's only approximation, and because of that, if we approximate our solutions, it tends to have some errors. So what are the sources of errors? We will discuss them. Actually, there are just two types of error that we will be discussing: the round-off error and the truncated error. But before we go, how do we approximate? So first, we need to refresh or review our, if you remember, significant figures. We need to know this before we can continue with our approximations. Significant figures, or sig fig. So if you remember them, good. If not, then listen. So what are the rules when we try to determine the significant figure of a certain number? So there are some rules that we need to follow. We need to consider. The first one: any non-zero numbers are significant. So any non-zero number, we consider them significant. Number 2, any zeros between non-zero numbers are significant. So if the zero is in between non-zero numbers, then we can consider them as significant figures or digits. The third rule: any zeros before non-zeros are not significant. Are not significant. So if the zero is before a non-zero number, then we don't consider it as a significant digit, except if there's still another non-zero after or before that zero, and that will be case number 2, or rule number 2. Rule number 4, we go now to number 4. Any zeros, so before, now after non-zeros without decimal points. Without decimal points are not significant. Then lastly, if there is a decimal point, any zeros after non-zeros with decimal point are significant. So to apply this rule, let's have an example. So I will give you the numbers. These are the numbers, and tell me what is the number of significant figure in this number. So first example, the number 17. How many significant figure are there in this number 17? So 1 and 7, these are non-zeros. So rule number 1 says that all non-zeros are considered significant. So how many significant? We have 2 significant figures. Next, how about 5,134.6? How many significant figures? All of them are non-zero again. So we can apply rule number 1, so all of them are significant. So how many? 1, 2, 3, 4, 5. There are 5 significant figure. Next, how about 101? There is a 0 in between 1 and 1. So what rule are we using here? So if any 0 is in between non-zero numbers, rule number 2 says here, rule number 2, any zeros between non-zeros are significant. So the 0 here in between 1 and 1 is considered to be significant. So how many significant figure do we have? We have 1, 2, and 3. Okay, that's rule number 2. Next, another one. How about 200 million thousands 7? So how many significant figure are there? There are so many zeros here, but all these zeros are considered significant. Why? Because they are in between 2 non-zero numbers, 7 and 2. So any zeros in between them are considered significant. What rule is that? Rule number 2. So how many significant figures are there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 significant figures. Next, how about 0.5? How many significant figures are there? We have here a point, a decimal point. So 5 is considered a significant figure because it's not non-zero. How about the 0 before that? So rule number 3 says that any zeros before non-zeros are considered not significant. So this 0 here is before a non-zero number, and after that there's no other digit before that 0, so it's not in between. So we can now conclude that this 0 here is not significant. So how many significant figures do we have? We only have 1 significant figure. Next, how about this one? 0.000000524. How many significant figures? Again, rule number 3, before. So these zeros are before this non-zero number. So we consider them all not significant. So if we count the number of significant figures, we only have 1, 2, and 3. So this is only a 3 significant figure number. Next, how about this one? 10,000. How many significant figures are there? So these zeros here are after a real number. It's not before, so it's after. So that's rule number 4, and it's without a decimal point. There's no decimal point after the 0. So we can consider them as not or not significant figure. So how many significant figure do we have here? We only have one significant figure. Then how about this one? 500. How many significant figure? It's also only one significant figure. Now how about 500.0? How many significant figure are there? It's the same as 500, but this time there's a decimal point. So how many significant figure do we have? We have 4 significant figure. It's not 1 anymore because there's a decimal point. That's rule number 5. If there's a decimal point, then you consider them significant figures. Then lastly, 0.031050. How about this one? How many significant figures do we have? So the first 2 zeros here are not considered significant because they are before a non-zero number. Then this 0 here is considered significant because it is in between a non-zero number. And the last one, the 0 here, do we consider it as a significant number? We consider it as a significant number, so it should be a 5 significant figure digit numbers. So that is significant figures. So I hope you know now how to determine the significant figures. Why do we need them? We need them later on when we try to determine our stopping criterion and iteration in solving some problems. So you need to indicate how many significant figure do you want your final answer to be. So if the problem says you can have up to 5 significant figures, so your solution, you give your solution to be also in 5 significant figures. So you should know how to determine the number of significant figures. Okay, so next, so after that, we also, before we go to the error, it's also related with the error. We first define accuracy versus precision. What's the difference between accuracy and precision? So first, what is accuracy? So how do we define accuracy? Accuracy refers to how closely a calculated or measured value to the true value. So how does your value compared to the true value? The closer you are with the true value, the higher the accuracy. How about precision? So the basic definition of a precision is it refers to how close or the individual calculated or computed or measured value with each other. So when we say precision, the true value doesn't matter. When we say accuracy, the true value matters. So we can also, if you want more analogous between accuracy and precision, here's another example. So if we have here a if I have here a dart or any the bull's eye then I throw some arrows here, and these are the marks of the arrows. So what can you observe with these arrows? How is my accuracy? It's not accurate. So this is not accurate. How about the precision? So the arrows are far with each other, so it's also not precise or imprecise, inaccurate and imprecise. How about if this is the result? I have here this result. So if you observe, they are within or close to our bull's eye circle. So we can say that this is accurate. My marksmanship is accurate, but we can also say that it's not precise. Why? Because the distance between these marks are far with each other, so they are not close with each other, and that's the definition of precision. So it's not precise. How about this one? How about this one? So the arrow marks are very close with each other, but they are not accurate. They are far from the bull's eye circle, so it's not accurate. But we can say that it is precise because the arrow marks are close to each other. Then how about a precise and accurate marksmanship? So if all the arrows is inside this circle, it's 100% precision, and it's also very precise. So it's accurate and it's precise. So that's the difference between accuracy and precision. They're not the same, they are different. Okay? So before we go to errors, or we can now go with errors. We can now define what is error. Or we can just cut this video. Let's continue to the next part. So this will be part 1 of chapter 1. Next will be part 2. Part 2 will be about all error, the sources of errors, and how do we solve errors, and what are the pre-specified tolerance or criterion that we know, and we will give some example.